Hi, thanks for the invitation. I'm Eiko Yoneki from University of Cambridge Computer Laboratory. I'm also a Turing Fellow at Alan Turing Institute. Today's talk is about auto-tuning using structured Bayesian optimization. It is for computer systems. I also briefly introduce the reinforcement learning-based framework at the end of my talk. Tuning computer system is complex. There are many configuration parameters. And what you want to tune could be performance of runtime, or power consumption, or accuracy of the result. There are too many knobs to make it right. Especially system environment is becoming more heterogeneous, where you need to consider vertical and horizontal scalability, cloud and/or edge computing, including specialized hardware accelerators. Here are some examples. Running deep learning application to perform training requires hyperparameter tuning. Cluster computing scheduling requires resource management of memory, I/O, and communication efficiency. Another example is LLVM compiler optimization on selection of the path list. Traditionally, domain experts tune the systems manually with offline analysis or using profiling. This is time-consuming, and once underlying software or hardware changes, they need to tune again. Distributed profiling is especially difficult. There is no clock synchronization guarantee and many resources to consider. If computer system takes a long time to run the objective function to evaluate, and the parameter space has a high dimension, it will take a long time to obtain optimal result. You can try dimensional reduction, but it may not work. Uninferential parameters may become inferential after the other value goes beyond a certain threshold. It is also important to understand the optimization model, including the input workload characteristics. Many systems problems could be combinatorial. Let's have a quick look at cluster scheduling for Tensorflow to see what is the parameter space looks like. You have an in-house cluster computing environment built by different machines. For example, some has GPU, some has a large CPU. You want to run ML training using TensorFlow over this cluster and to obtain the best from this small cluster. TensorFlow doesn't have an automated load balancing capability for heterogeneous machine setting. Therefore, you need to write your own scheduler. Let's pick up 3 parameters to tune: which node to use as a server, worker, and the batch size as one of hyperparameters. Individual machines' computing model, communication models, synchronization between cluster nodes, depending on input network, need to take part of tuning. This sums up setting over 30 parameters, and it will create a large combination of configuration space. It is too hard to deal with a large parameter space manually. The idea of auto-tuner, black box optimization tool has emerged. Some examples of auto-tuners are listed here, from random sampling, evolutionary approach like Databricks, to OpenTuner, which uses hill climbing approach. For specific to ML hyperparameter tuning, the variation of random search shows budget-efficient result, such as hyperband. The recent work based on Bayesian optimization demonstrates sample-efficient auto-tuning methodology. How does Bayesian optimization work? BO is an iterative operation. First, find a promising point for high-performance configuration in parameter space. Then evaluate the objective function at that point. After the evaluation, update the model to reflect this new measurement. In each iteration, the probabilistic model of objective function is updated, Typically, Gaussian process is used as a probabilistic model. Bayesian optimization has a limitation known as the curse of dimensionality. It doesn't scale. It's depending on the condition, but beyond 10 dimensions, it will not work well. Dealing with computer systems, we need more than 10 parameters. To deal with high dimension problem, we came up with the idea of structured Bayesian optimization. Let's call it SUBO. In SUBO, instead of using Gaussian process, we use a probabilistic model written by a systems expert that reflects the parameters' behavior, such as relation between parameters. But it is not necessary to have a complete model here. The good prior reflecting systems behavior helps to understand the trend of the objective function and the high precision in region of the optimum. We provide a novel probabilistic C++ library to let the expert write this probabilistic model. The semantics of probabilistic C++ is based on probabilistic C from Oxford. It became a few hundred times faster than the original probabilistic C. On top of SUBO, we built a framework called BOAT for the developers to build their own auto-tuners. For the inference algorithms, currently only sequential Monte Carlo SMC is implemented. SMC will perform poorly with too many draws at once and with no observation in between. Many probabilistic programming languages offer access to various inference models, such as Gibbs sampling or variational inference. Different inference will be best suited to different types of models. We plan to extend probabilistic C++ and or implementing the equivalent functions in different probabilistic programming languages. SUBO provides semi-parametric model. Parametric model is like a linear regression, and non-parametric model is such as Gaussian model. We combine both to take advantage from them. Direct acyclic graph DAG template is provided for writing semi-parametric model. The model allows the users to construct a subcomposition where you can write a hierarchical model. Semi-parametric model is defined as a prior for SUBO. The non-parametric model is used to model the difference between the parametric model and the observed data. Currently, we have our own GP implementation, but the user can provide own version of a non-parametric model. DAG network structure is used for independent optimization. Each node performs its own optimization, and each node only sees its own input and output. Let's look at the JVM's garbage collection over Cassandra for optimizing 99th percentile latency. We tune 3 parameters of CMS collector, the young generation size and the survivor ratio flags, which manage the size of the heap, and the max tenuring threshold, which sets the rate at which objects are promoted between heap selections. Essentially playing with the heap size and the garbage collection execution timing. This is the DAG of garbage collection. Blue nodes present the individual optimization unit. Furthermore, during numerical optimization stage, the composition mechanism can divide optimization to smaller optimization process to take the advantage of nesting structure for improving the performance. This is an example of probabilistic C++ describing DAG model of garbage collection. 3 models are defined. This shows one of the leaf node GC rate model. Both parametric and non-parametric models are described here. Quickly, I show the result. Purple bar is the SUBO approach. This plot demonstrates that both optimization gives performance improvement against Cassandra's default setting. JVM's GC is an important component, and it is supposed to be well optimized. However, this result shows it has still some space to optimize by the help of AutoTuner. How about the performance of optimizing process itself? Here, OpenTuner is based on hill climbing approach with a combined 10 different optimization techniques. Spearmint is BO-based approach. Both reaches the optimal point in 10 iterations. Let's look at the distributed scheduling of Sgd over TensorFlow, which we looked at the scale of a parameter space before. Here are 3 parameters to tune: what to use as server worker and input batch size. Individual machines, computing model, communication models, network speed for synchronization between cluster nodes take a part of tuning. Probabilistic model can include something like longest execution time in the overall time of final execution time. Such intuitive thing takes many iterations to figure out for the standard GP-based BO. But Subo can take advantage of such information to shorten the optimization. In this plot, as you can see, optimization by both converges in 10 iterations. OpenTuner and the Spearmint do not converge. Y-axis is the runtime of Sgd with a median of a best configuration found across 3 trials. Overall tuning with both finishes the 10 iteration within 2 hours in our experiment. So this plot shows random search wins to Bayesian optimization over the optimization of a LLVM compiler path list. It is standard BO, not even a Subo. Objective function is runtime performance. LLVM has internally modular-based operation, and it is like a sequential module selection among the sets of options. When we are going to apply both to LLVM, we realize that this optimization is a combinatorial problem. It is a problem of selection, either a single option, an ordered subset, or permutation from discrete options. Cluster scheduling features similar kind of model. The goal is selecting from jobs from a queue to be scheduled next, and which resource to be scheduled to. Another example is selecting a combination of attributes to index from a list of attributes in database, such as for MongoDB. This made us to investigating the use of reinforcement learning to solve this kind of problem. Probably most of you know reinforcement learning. The basic setting of reinforcement learning agent interacts with an environment, can take actions, observe the reward and the new state. Unlike BO, it's not a static setting, but decision-making under varying workload. Agent actions affect the subsequent information it receives in future. Here is a brief history of RL tools. More, I would say, the deep reinforcement learning tools. Big progress was made by OpenAI Gym, a unified benchmark interface for many different tasks, and the reference implementations. However, it is still a loose collection of algorithms and no efficient way of thinking about execution APIs yet. RL-Lib, Ray by Berkeley, enables simple declarative interface for applications and scalable distributed execution. Still, many problems remain, and the execution and algorithm logic are tightly coupled. Building software for RL is hard. Decision problems in systems has extremely large action space, Simulation work is expensive to build and it is often oversimplified. Unlike supervised learning, there is not a single dominant execution pattern. Algorithms are highly sensitive to hyperparameters. So here we introduce RL-specific framework called RL graph. It provides a systematic mechanism to construct high-performance RL computation graphs. The idea is a separation between logic of RL computation graph from back-end dependent implementation. It automatically builds the data flow for underlying execution engine from RL computation graph. Created data graph can be transformed to support different device strategies such as much GPU. Separation of distributed execution and the local device management. It can also build arbitrary subgraphs and test data flow, which makes it easier to identify potential implementation problems. So these plots show the comparison against Ray RLDeep, which is a prior state-of-the-art performance on Apex distributed Q-learning. The exact same algorithm logic, hyperparameters, network size, hardware are used, yet RL graph is much faster. The reason why it is faster is mainly it comes from we uncovered from systematic data flow analysis, which brought more efficient implementations. RL graph helps most in improving high-level data flow as it forces well-defined interaction between components. Okay, summarizing my talk here. Key message is data-driven RL machine learning approaches help systems optimization in complex parameter space. Key idea here is decomposing and structuring the performance model and/or action space to optimize the optimization. These are the references. Thank you.
This was extremely interesting and a great transition from the previous talk. As I've already mentioned, I was curious about whether it's possible to apply some dynamic optimizations for data structures. But first, I'm gonna ask Giovanni's question. So I was wondering, how do you manage noise in the results coming for performance tests?
That's the greatest part of using this probabilistic programming. So it comes with the inference algorithm and all combining with the Bayesian optimization. These noise are essentially considered sort of noise. And internally, we came up like a very sophisticated, not completely, like optimal, but the numerical optimization. And inside of this numerical optimization, we use actually reinforcement learning or evolutionary approach to get the, like a more optimal high performance point. So which essentially eliminate all the disease area.
Awesome, thank you. Stefano added, like, if this approach can be applied to line settings, production. And I want to extend this question because it's somewhat related to the question that I had. So, for example, if it's possible to use this approach, or if it was tried for something like JIT environment, or when let's say you have a lot of services, you usually put them under load balancer or whatnot, and then you can potentially use different configuration parameters to launch those services behind the load balancer, dynamically monitor for the optimal configuration, and then based on that, decide what is the most optimal configuration. So you basically don't use like a synthetic environment, but you use like a production environment to capture the data. Have you used this approach?
Yes. So So it's not really a synthetic environment. So you are talking about both a Bayesian optimization-based approach, right?
Yes.
Are you talking? Yes. So the Bayesian approach requires sort of like a, continuous model on the workload, incoming workload, because you have to have some kernel function in the BO. So, our experiment environment is not as big as like Amazon environment, anything. But anyway, we run in Amazon environment or actually GCP environment. So you can do it online. So that's it's a matter of scale of environment. So when you apply this both approach, if running execution of one run, objective function evaluation, is shorter, it just doesn't make any sense at all because the complexity of logic behind really kills you. But if it's longer, as you saw, most of the cases, it converges within 10 iterations. We tried a bit of different case studies. So you can apply on online environment with, I don't think, any problem. Did I answer your question? So you want to create like an online environment. The one environment, this one might have a different workload. Other environment, this one might have another workload, and you do different experiment, getting configuration parameter, and then you play with that or something like that. Or can you rephrase?
Yeah, that's what I meant. Like I guess.
Well, so what's the difference over each environment?
Well, the configurations, like for example, let's say you want to see what is the best GC configuration. So you use different configurations. Like for one service, you use one GC configuration. For the other service, like for the exact same copy of the service, behind the load balancer, you use a different configuration setting for GC.
Yeah, okay, so yeah, of course you can do it. And we actually added, it's called a multi-objective BO, so which means you can have a multi-objective function. So then you can see, like a comparison, what influences on different configurations. So what you can play with when you decide a configuration among 3 different configurations. So that might help.
Awesome. Thank you. That's great. We have one more question. How do you deal, from Alexander, how do you deal with regressions on your models? E.g., if model was performing well in one environment and at one point of time, but quickly deteriorated when something changed in environment. Performance engineers often find it hard to understand the reasoning why a certain parameter was tuned with black box testing.
Right. I think, so that's so if you are in a data center environment or something more dynamic environment, incoming workload changes, and which really changes the configuration setting. That's much more for reinforcement learning kind of approach is necessary. To do Bayesian optimization, you have to have a continuous modeling of incoming. And because of like some kind of virtualization, some memory changes internally, and that would change your configuration parameters. In that case, you have to put in that bits of information as a part of this model. The one way, if you do this both optimization tool running, and if you don't get the result, then you have to bit to play with, like adding some more parameters. So otherwise, you are dealing with a very dynamic environment, and memory or some allocation changes all the time, which is not taking a part of this optimization. Then this would not work. Make sense?
Yeah, I think so. That definitely makes sense. Let's see if there are any more questions. I think it's just in general, there are always questions around black box testing. It's like, AI and machine learning usually, like depending on the technique that is used, it sometimes makes it a little bit opaque to understand what exactly were the factors. And so I think convolutional networks usually provide you with some sort of pictures for images. Like, for example, what are the features that they were using for detecting certain parameters. So I guess it's just a common challenge for pretty much all machine learning algorithms, and ability to communicate the reasoning behind choice is not always straightforward, but what you say makes sense.
But here, this both approach is, so if you just use the Gaussian process, then it's like a kind of complete black box. You just don't know from X input, Y output comes out. But the point here, which we want to make, is we have to make some, human input. How we can encode that human expert input, because the expert knows a lot, complicated stuff in simple way. So to put that information as a part of black box process and to make it a bit of like a gray box. So, but we are talking with machine learning theoreticians, but they can come up some kind of like a theoretical proof. But how actually we can integrate this and to make it as a framework was nobody before came up. And so this approach, like using probabilistic programming, is a kind of newish, and it would really help. And it's a long way to go to refine, but that's kind of an intention to to really understand what could be a good knobs and to play with to obtain the best configuration. Of course, original idea is, okay, so a long time ago, how can we get the best optimization of map reduce in a distributed very large environment? Quite impossible, so many regression parameters. I don't think this work is meant to reach that point yet, but it's a quite unique work for us.
Well, I hope you're gonna crack this nut. I'm very much looking forward to see even more developments from this work. I think it's super exciting. I think it's gonna help us to deal with a lot of complexity. Our systems are so complex, like compilers, for example, GCC, I think has more than 2,000 command line flags, and each of those flags can have a pretty significant impact on performance and program execution characteristics. So I'm very much looking forward to see the progress in this area. Thank you so much for working on this. Thank you for joining us. And we're gonna make a small 1-minute break, and we are gonna continue our summit with Alexander's talk on optimizing application binary size on mobile. Thank you so much again. See you in 1 minute.